In this class, we will discuss a problem on a C-section, cold formed steel section, to compute the section modulus of the effective section in bending. That means Z value. How to compute the Z value of a CFS section, cold formed steel section, for the effective section. So that means we have to find out the effective width and all as per the code, and then we need to find the moment of inertia of the effective section. Then we have to divide that moment of inertia by the distance of the farthest fiber to get the effective section modulus. Now the question is like this. This is the C section which is given. Overall dimensions are given here. 65 mm is this for the flange, 220 mm for the web, and for the lip it is 15 mm. Thickness throughout it is uniform thickness 2 mm. So radius here is 1.5 times the thickness, that is 1.5 into 2, 3 mm. And the value of yield stress is given as 280 Newton per mm square. The compression flange is subjected to local buckling. Only the compression flange is subjected to local buckling. That is the assumption he has given. And the value of this FC value, compressive stress value, can be taken as 0.8 times Fy, which comes out to be 0.8 into 280, 224 Newton per mm square. And these are the midline dimensions. You can see here midline dimensions means if you take like this, so this is the midline dimensions. So out of the 65 you have to deduct 1 mm this side, 1 mm this side. So 63 it becomes. Here also 220 minus 1 minus 1, and here 15 minus 1 mm. So this is 1 mm. So 14. So this is the midline dimensions. Now the procedure is like this. First we have to calculate the limiting stress or the maximum stress for the stiffened web in bending. So in the last video also I have explained about this. It is given by this formula. P0 is equal to 1.13 minus 0.0019 dW by T root of Fy by 280 into Py. So this is there in page 17 of the BS code. So BS code is also allowed in the examination. BS British Standard Code 5950.5. So refer page number 17. So here dW by T let us calculate. So dW is the overall depth of this web, which is 220, divided by thickness of the web is 2. So it becomes 110. So 110, this is the comparable value, it is greater than 68. So we have to calculate this P0. Suppose if this is less than or equal to 68, then this P0 value will be equal to Fy. So that is what the code says. Otherwise you have to calculate P0 value using this formula. Since it is greater than 68, we have to calculate P0 using this formula. Now we need Py also. Py is the design stress, which is given by Fy by gamma mb. So partial safety factor is 1.15. It comes out to be 243.447 Newton per mm square. Now substituting these values in this, we get 1.13 minus 0.0019 into dW by T is 110 into root of Fy is given as 280 by 280 into Py value is 243.47. If you simplify, you will get 224.24 Newton per mm square. In the second step, let us calculate the effective width of this compression flange, because in this problem he has given that only compression flange is subjected to local buckling. Let us see how we can calculate the effective width of the compression flange. So this is the compression flange. So top one is the compression flange. So I will equate the neutral axis here, passing through the centroid. So this becomes the compression portion, and this becomes the tensile portion. So now let us follow the BS code now. As per the British Standard Code, Part 5. So it is the equation is given in page number 12 of the code to calculate the effective width. So for that we need to compute a parameter called h, which is the ratio of B2 to B1. So B2 is the width of this web portion and B1 is the width of the flange portion. So it is like this. So you have to refer the earlier videos to understand about that. So this is B2, this is B1. So now B1 is here, the overall width is 65. From that you have to deduct 2 times the radius minus 2 times the thickness. So that gives your B1 value. B2 value is overall width of the web minus 2 times the radius minus 2 times the thickness. So it comes out to be 210 now. Take the ratio 210 by 55, it is 3.82. Now you have to compute what is called as the buckling coefficient. You know that for the buckling coefficient, the minimum value in the code for stiffened element is taken as 4 and the minimum value for unstiffened element is taken as 0.425. Now here, since this becomes a stiffened element, because both the sides are laterally supported, so here you can take this formula, K1 is equal to 5.4 minus 1.4 h by 0.6 plus h minus 0.02 h cube. Substituting the value of h as 3.82 and simplifying, you are going to get 3.07 as the answer. But as per the code, the minimum value we have to provide is 4. Therefore, take K1 as 4. If this K1 value is greater than 4, that value you have to take. If it is less than 4, you have to stick to 4. Now we have to calculate one stress value called PCR, elastic critical stress value. Once again, that the equation is available in page number 12 of the code. Of course, he has given 0.904 E. So E value you can take 2 into 10 power 5 or 2.05 into 10 power 5 Newton per mm square. And if you substitute here in this, you will get approximately this value into K1. K1 is 4 you have to take now, into T by B. T is 2 mm thickness and B is, we are calculating for the flange, therefore B we have to take B1, which is 55. So this B becomes B1 here. Now if you substitute and simplify, 980 Newton per mm square, it is the elastic critical stress value you are going to get. Now after having these two values, FC and PCR values, we have to calculate this ratio B effective divided by B. It is available in page 12 of the British Code, part 5. Use this equation here. You know all the values in the RHS. So what happens, I will calculate FC by PCR now. FC is 224. Here you know, divided by PCR is 980. The ratio becomes 0.228. So you have to compare that ratio with this value 0.123. Since it is greater than 0.123, this formula we have to use. That's what the code says. Now if you substitute the value for FC by PCR 0.228 minus this value 0.35, 4 to the power of 4, 4 to the power of minus 0.2, so almost you are getting 0.99. So B effective now will be equal to 0.99 into B. B is here once again B1. So almost 54.5 mm you are going to get. That means out of that 55 mm, only 0.5 mm is ineffective. So for 54.5 mm is effective. Now you can rewrite the section. So here I have written the center line or the midline dimensions similar to this. Only thing is here, this becomes 218, this becomes 63 only because this is tension. This is the tension flange. Since this is tension flange, there is no change in the effective width. Whereas in the compression flange, instead of 63, so what happens here, 0.5 mm becomes ineffective. So this middle portion here, the small portion becomes ineffective. The rest of the dimensions are distributed. Now total is 63. Since total is 63, divided by 2, 31.25, 31.25. So it becomes, this is the effective width, and here all these dimensions remain the same. Now after writing this effective section, now we have to compute the moment of inertia of that effective section. So you can use any method. You will be having two neutral axes. The top one which I call it as XX axis, that is the neutral axis for the cross section for this section. Cross section means for this section. Whereas the bottom neutral axis is the neutral axis for the effective section. That means for this is the effective section. So if you calculate if you locate the centroids G for the cross section and G1 for the effective section, you will be having some eccentricity, some vertical difference will be there here. That eccentricity you can find out that it is 0.15 millimeter. That I have explained in the last video. Please go through that. So same procedure is adopted here. In last video I have done for this type of section like this. So similar same procedure you can follow for this also. So then you have to compute the moment of inertia for this effective section. So which comes out to be 4.9 × 10⁶ millimeter per 4 about this x1 axis. So that also I have explained in the last video. Please go through that. Once you get the value of effective moment of inertia of the effective section about that x1 axis, now you can compute the section modulus of this effective section modulus. You can say section modulus, or you can take it as effective section modulus as the ratio of moment of inertia to the farthest fiber. So farthest fiber is this one. So the distance from here to here, the farthest fiber becomes 218 divided by 2. So if you simplify this, you will get 44.96 × 10⁻³ or roughly you can take it as 45 × 10⁻³ millimeter cube. That is the section modulus of the effective section for this section. So afterwards, if they ask you to find out the moment carrying capacity of that section, multiply that effective section modulus by the stress value. So that stress value, of course, it is FC value, which is 224. You will get the value in Newton millimeter. Finally, you can convert into kilonewton meter. So for this problem, you are getting the moment carrying capacity of this particular section as 10.08 kilonewton meter. Suppose if they give the span, you can always find out the load that can be applied on that particular section for that given span. So just like last problem what I did. Suppose if they ask UDL, you have to equate this W to M to WL square by 8, and you can find out that W. If it is central concentrated load, then WL by 4. So M is equal to WL by 4. L you will be given. So you can find out the allowable load that can be applied on that particular section over a particular span. So this is how we can compute the effective section modulus for a given cold formed steel section. So two problems I had explained, one for the C section, another for this type. In the examination, they may ask you to find out the section modulus, or they may ask you to find out the moment carrying capacity or the load that can be applied. So this is the basis for the design of beams using cold formed steel sections. So normally in the case of designs, they will give we will be knowing the moment shear values. So for that we have to assume a suitable section, and we have to cross check whether the section is safe against both bending and shear, all those failures.